using a click versus a rising frequency chirp stimuli for listening to AVRs in infants as well. So I have to say, I have to put it out there, I'm actually nervous presenting today. I like to present, but I'm nervous today. That's okay. All right, so a little bit of background, of course, on the research. So this research was part of an innovations grant that was investigating sort of new methods of assessing hearing in awake and non-sedated infants. And so specifically, I was trying to determine the efficacy of using a rising frequency chirp as an alternative stimulus for recording AVRs in infants. So just to back up a little bit to kind of get everybody up to speed on AVR. So an AVR is an auditory brainstem response, which is a test of neural synchrony. And that neural synchrony allows us to estimate hearing thresholds, is what we use it for. So, thank you. So it's not a hearing test per se. It's kind of often a misconception is that it's a test of hearing, but not really a test of hearing, but more so that allows us to assess the ability of the auditory nerve to fire in a synchronous manner in response to an acoustic stimulation. So it's an electrical response to sound, which is measured by a series of sort of 5 to 7 waves. We're most concerned about the first 5 waves, are what we're really concerned about. So these waves have peaks, and the peaks are labeled using this kind of conventional Roman numeral system as well. And while there are a variety of components that we look at with the AVR, we are most interested in latency. Seems to be kind of the dominant characteristic that we're assessing. We're always very concerned about when these peaks are occurring, how much time is in between the peaks as well. But we also look at the amplitude of the response. So we want to see how big the waveform is, wave morphology, always see how pretty the wave is. And then, of course, interaural agreement. How, are the ears balanced and equal? So, well, I said that the first 5 waves are the waves that we're most concerned with. Of those first 5, wave 5 is sort of our landmark. It's typically the most stable wave, and it's the most robust. So it's the biggest wave. It's the easiest one to identify. There is a correlation between the stimulus intensity and amplitude. So as we reduce the stimulus intensity, so as we make it softer, our amplitude gets smaller. And also there's a latency. Again, I said latency was very important, but there's also a systematic latency shift as well. As we decrease the intensity, the latency kind of shifts out as well too. But even at reduced levels, intensity levels, so near threshold, that wave 5 is the one that's sort of the most identifiable of the waves. So that's the one that we're always looking at as wave 5. So the take-home message about AVRs really is they're a non-invasive objective test that we use to estimate hearing thresholds, mainly in populations that are unable to provide reliable behavioral information. That's what we really want is behavioral information. We want to put you in a sound booth, and we want you to raise your hand when you hear the beep. But some populations we can't do that, specifically infants. So with infants, the only thing that we really need from them, the only thing we really need from a subject when doing an AVR is we just need you to be quiet. We just need you to kind of zip it, So an adult is easy. If I put you down, you say, great, just be quiet, you'll do that. Interestingly, infants are not quite as cooperative. So that was a challenge for sure. Okay, so again, continue on with AVR. So the challenge with AVR, of course, is that the brainwave response that we're recording is very, very tiny compared to surrounding noise. So Dr. Cohn, where's Dr. Cohn? She always says AVRs are all about signal to noise. All about signal to noise. So that's what we're always trying to, that's always the challenge is getting the right balance of signal to noise. Now, noise can come from a variety of places. So it can just be ambient and environmental noise. It can be electrical noise. It can be myogenic noise as well. So you have this noise, and we're putting in this stimuli. We're putting in this signal, and we want that signal to be a lot bigger than the noise so that the auditory, so that the nerve fibers and vascular membrane are going to respond to it. So up here, so this is a click AVR. So here we are at a nice high level. This is 90, working on its way on down to 40. So just to remind you that there's our wave 5, so it's marked really nice. You can see there's other peaks up here in the beginning as well. But here are these systematic shifts that we see as we decrease in intensity. You see the little bit of a latency shift that this wave 5 peak kind of keeps getting pushed out further and further as we go down, but you also see the systematic decrease in the amplitude as we go down as well. So while up here you have your nice wave 5, and you see these other wave components in here, as we decrease in amplitude, those first couple of waveforms drop away, but wave 5 sort of remains. Even though it's been diminished, it's still the most easily identifiable of the waves in there. Now, if you think about when we're putting in, so up here we have a really good, kind of signal to noise ratio. We put in a signal, it's a really nice high level. All the auditory nerve fibers are like, yes, we hear it, we hear it. And so they respond, even though you might have this noise going on, at the same time. Now, as we decrease in intensity, so as we start to make that stimulus softer and softer, I think the thing to remember is that essentially the noise remains the same. That doesn't decrease. So then that's why your signal to noise ratio starts to get worse. So up here, really high signal level, really good signal to noise ratio. As we get closer and closer to threshold, less nerve fibers are responding to that soft sound in there. So our signal to noise ratio is poor, and it makes it more difficult to identify that response at those soft levels. So our goal ultimately is to do anything we can to reduce the noise or make the signal bigger, or both, obviously, to make it easier to identify that neural synchrony in there. Now, there's a variety of recording techniques that are used to minimize noise, but ultimately for us, what we said our question really was, okay, well, there's all these recording techniques available to minimize noise, but can we use the stimulus can we optimize the stimulus to obtain our threshold? So can we increase that signal now? Okay, so what we use right now is the click. So I always call it the clickety-click. Just so clickety-click. It does, that's what it sounds like. I always describe it. That's what it sounds like. So, okay, so the click. So this is what's conventionally used right now. So the click is an abrupt stimulus. So it's this broad frequency spectrum, abrupt stimulus with this really fast onset and offset, with the idea being that it evokes this whole nerve action potential. You throw in all the frequencies at the same time, really hard, really fast, and the whole basilar membrane responds. You get a huge synchronous response from the nerve. Great, that sounds awesome. So we said, we love the click. We're not here to talk bad about the click. Click is our friend, it's reliable, it's tried and true. I mean, in 74 is when he talks when Lambos first said, hey, I think that ABR can be used to estimate hearing thresholds in infants and adults. So we've got 40 years of using ABRs. Lots and lots of normative data is available on it. We can feel really confident about interpreting the results that we get based on all of this data here too. And again, the responses are really easily identifiable at a super threshold level. So the click, we love the click. But having said that, there's always things that we can do better, right? There's always things we can improve upon too. So while we say that the click elicits a whole nerve action potential, in reality, it actually gives us a more narrow frequency response. And that really has to do with, we kind of say, hey, these mechanical response properties of the basilar membrane. The basilar membrane has different mass and stiffness properties, qualities about it. Meaning that even though you might throw in acoustic stimuli all at the same time, it doesn't really mean that the basilar membrane responds at the same time. You've got the high frequency fibers are going to respond a lot faster than your low frequency fibers, which means that they sort of dominate over the response. So while everybody's going to get some information, those guys with the high frequencies are going to kind of have a bigger say in what the response is. I was trying to think of an example, and one thing I can think of was Congress and how you have congressional representatives. In the Senate, you have every state gets two senators, right, equal. But in Congress, it's based on your population, right, your state population. So while theoretically everybody gets to have an equal vote on an issue, the states that are bigger, and have more representatives, ultimately, get to dominate the response and the outcome as well. So that's us. So high frequency fibers are like California, I guess. Yeah, right, I know, I thought it worked. I was like, I think that kind of works, actually. I don't know why I thought of it, right? So anyway, so again, thinking about signal to noise ratio again, everything's still always coming back to signal to noise ratio. So the click, we still have this issue of kind of a poor signal to noise ratio near threshold. It's because so already low signal, so low intensity level means fewer nerve fibers are already responding. So you already have a reduced response. Now you couple that with an even more narrow frequency range is responding, and so again, you're just reducing your signal to noise ratio more and more as you go along too. So while wave 5 again is our most easily identifiable one, we still have these kind of issues of limitations, I should say, with the clip. So this graph here, this just represents the frequency response time across the basilar membrane. So we have, frequency across the bottom here, so low frequencies, on up to high frequencies, and then time along the y-axis. So certainly what this shows is that our high frequency fibers respond much faster than the low frequency fibers across stimulus level. So again, while all the energy is maybe being put out there at the same time, those different mass and stiffness properties actually result in kind of these time delays by frequency response. All right, then our pal, the chirp. Chirpy chirp. I'm going to call it the click, I'm going to call it chirpy chirp, right? So we didn't put it in here, we often called it clerp because we would often get it so often. I was going to make t-shirts that we had buying, so our new guy, okay, so the rising frequency chirp. Okay, so this great quote kind of here by now. The rising frequency chirp is designed to produce simultaneous displacement of the cochlear partition by compensating for frequency-dependent response time differences. So, rising frequency chirp is exactly what it sounds like. It's going to take low frequencies first and present an upward sweep to your high frequency. So it gives you this rising frequency with the idea being that rise by presenting the low frequencies first is going to help to compensate for the travel time differences across the basilar membrane. So essentially, you're just giving the low frequencies a head start. So let them get started first. By the time they get moving, because those are like the little fat, heavy guys down there. Like by the time they get moving, the high frequencies receive this information, and then everybody really responds. So the goal there is that you generate an even more synchronous neural response and an even more robust response. So the big thing that we see, we don't really see changes in latency, but what we see is a much bigger amplitude response. So again, kind of representative of that signal to noise ratio too. So hoping that that's what we can optimize. Okay, so looking at the stimuli here, just to kind of compare the stimuli. So here we have our click and our chirp down here. So you can see here's the waveform. Here's your really fast, rapid onset, offset, kabam, and hit there. It's 100 microseconds. It's super, super brief. And then here's our rising frequency chirp. So you can actually see the rise in it. But this is a much longer duration stimulus to allow time to start from lows and sweep up to the highs. So that's a 10 millisecond stimulus presentation. And then over here we have the in situ information to demonstrate the acoustic information that we're getting about. So ultimately, so what you should really see here is that while these two look very different from one another, over here, spectrally, they're not that much different from one another. So what that tells us is that the chirp is probably really viable to compare to applications where we use the click because they're so spectrally similar. The other thing it tells us is that any differences we might see in the response are likely not due to spectral differences because there aren't really significant spectral differences. But more so, it's probably in the mechanics of how we deliver the stimuli. So both of these guys are still stimulating a huge frequency range. It's just how we do that we're changing. Fast, quick time to do that, or a little bit slower, sweeping from low on up to highs. All right. Hello, our little adorable test subjects, right? This is one of our test subjects as well. So he's an adorable little guy. Okay, so here's what we have so far. So subject to 9 subjects, 7 males, 2 females, ranging from 8 weeks to 39 weeks in age. For all of these infants, we did an ipsilateral right ear recording only. We used our Intelligent Hearing System, Smart EP system. We used a 3-electrode montage, so using Vertex and then mass toys as well. Because we have all of our filter settings and stimulus and all that kind of stuff in there too. And then we compared the click and the chirp in there. So one of the things that we think sort of is unique or special about what we did too is that all of our data is same subject. It's comparative data within the same subject. So we didn't just collect chirp data from some babies and then bring in different babies and collect click data from them. We were able to obtain click and chirp data within the same infants, and we did it within the same test session. Not that we were opposed to doing it during different test sessions, but we did it during the same test session because just as you start testing babies, you realize, of course, that they're really running the show, and you have to just get as much information as you can, as quick as you can, as well, too. So we think that that's a good thing. So everything we have is comparing same subject, same day session, so that any kind of variability, things especially like signal to noise ratio, should be pretty comparable, because I might literally have been like a 70, a click at 70, and then a chirp at 70, and then a click at 30, and a chirp at 30. I always went back and forth so that I was always obtaining the same information too. So, all right, so here we have, of course, our infant. This is a rising frequency chirp AVR response for an infant. So here's where you can start to see that we have this is sort of our stimulus duration. So that's the presentation of the stimulus in there, and then we start to see our peaks in there. So this is, just take my word for it, that's a really big wave 5 over there, too. I think the thing to point out here now is that this is 70, and for us, we obtained our recordings at using dB peak-to-peak SPL. And so typically in clinical audiology, you're going to, the final number you're going to get your AVR results down to is going to be a dB NHL, which is a behavioral correlate. Ours is at a peak-to-peak SPL. The correction factor we serve Bourn to is about 20 dB, so it equates to about 50 dB NHL. So that's one thing that's going to kind of come up here again, so it's just to remember, and I'll remind you about that, is that 70 isn't really 70, 70 is actually 50. Okay, so again, this is just more sort of the same data, just showing here's the chirp and here's the click at 70. So you can sort of even see here. So this is just where you can just see sort of the difference. Here we have this kind of stimulus time period where the stimulus is being presented, and then here come our waveforms. And then down here with the click, more on our sort of traditional, conventional latencies that we're expecting to see as well. So, okay, so now we'll do the side-by-side comparison. So this is in a 4-month-old infant, and so this is click data. So this is a beautiful click response. This is great. So this is starting at 70, working all the way down to 20 SPL. So beautiful response. So again, we see everything we expect to see in normal hearing too. So nice big robust response, and then we see a systematic latency shift, a little bit of a shift down there as we decrease the intensity level, and then we also see the amplitude decrease systematically as we go down. So nice big amplitude up here, much smaller amplitude down here, and a very soft level. Now here comes the chirp. Here we go, chirp, right? So much bigger. So the big thing you can see right off the bat is a much bigger amplitude response. Just subjectively, you see that. Okay, wow, that's a much bigger one. But like I said, this is a fantastic quick response. So this is a fantastic chirp response as well. So same thing, systematic latency shift with decreasing intensity, systematic decrease in amplitude with decrease in intensity as well. And so down here you might say, okay, well, maybe the chirp is a little bit bigger than the click, right? Okay, it's a little bit, but I don't know dramatically. But this is where we have to remember what these levels actually are, is that 20 is actually 0 dB NHL. So Dr. Norris, we were talking yesterday, and she was reminding me that clinically, as an audiologist, you would probably only ever go down to 20 dB NHL anyway, because that's normal hearing. And you're not going to keep going below normal when you're testing for an AVR. So she was saying, it's actually much better to look at 40, because 40, you apply the correction factor, 40 is actually 20 dB NHL. So now we're like, okay, here's normal. So now you start to look at 40, and now you see a much bigger difference between the amplitude response. Again, just subjectively, you just say, wow, that's a much bigger response. Now again, this is normal hearing, and this is certainly a spectacular response. But even though it's a spectacular response looking across intensity, it was not an unusual response, right? I don't think it's an unusual response from what we saw. It's not like, wow, this one was way better than everything. This was not atypical from what we saw. It just happened to be a little bit all the way down. Now, I did run this baby at 10 dB as well, just to see, and there was no response at either the click or the chirp either as well. So. Okay, so this rising frequency chirp advantage, this just demonstrates what we just talked about, really. So just saying that the rising frequency chirp does have a wave amplitude advantage. diminish as we get down to, as we get through lower levels and get closer and closer to threshold. And so the question, of course, is, well, why did the advantage diminish? Why do we think that is? So a few things. So one, thinking natural filtering of the ear. Okay, so there's sort of progressive filtering that already goes along with the ear. So we were just saying that, we know that, oh, if we put in a 70 dB SPL stimuli, that everything below the red line is going to respond. And as we get lower and lower intensity, there's less nerve fibers being stimulated, so less error in response. Then you couple that with a reduced frequency response, and you're getting a more and more reduced response in there. So ultimately what's happening down here, so the click, you remember the click has a narrow frequency response already, so it's already down here. So when we move down to low intensity level, the chirp becomes actually much more click-like, so they start to have a much more similar response characteristic, therefore there isn't going to be a difference between them. The other is a 100 Hz high-pass filter. So we actually kind of made an oversight that when we did, previously when the adult data had been performed, there was a 100 Hz high-pass filter used. Typically with infants, you use a 30 Hz high-pass filter. It allows a more low-frequency information. Babies are very low frequency, the mass-dominated beings have more low-frequency information to get in there. So we're like, well, gosh, maybe could that be it? Maybe we were losing some information down there. But we actually experimented using the 30 Hz filter, and we didn't notice any difference at those low levels too. So we didn't notice any difference, so we don't think that it actually impacted that. But we were consistent. All of our babies have used the same filters. We didn't change anything as well. Once we got a protocol that it wasn't completely out of line, we always decided to just stick with it too. And the other thing is that there's just reduced data points below